Hi, my name is Cedric, and today I would like to talk to you about the strongly polynomial algorithm for linear programs with at most two non-zero entries per row or column. This is joint work with Daniel Dadouche, Bento Natura, Neil Olver, and Laszlo. In this talk, I will start by introducing linear programs and defining what a polynomial and a strongly polynomial algorithm is. Then, we will focus on the subclass of LPs with at most two variables per inequality, and show how this class of LPs reduced to a well-structured problem on graphs called the minimum cost generalized flow problem. Then we will present a strongly polynomial interior point method for this problem. A linear program is the problem of optimizing a linear function subject to linear inequalities. This is the dual LP on this slide. The primal view of a linear program is to minimize a linear function subject to being in an affine space intersected with the non-negative ordinate. Linear programs are introduced by Kantorovich, Hitchcock, Koopmans, and Danzig back in the 40s to model economic production and military operation problems. An input to a linear program is the constraint matrix A, which is n by m, the right-hand side vector B, and the cost function C. We will also use L to denote the total bit length, which is the total bits required to encode the numbers in A, B, and C. A polynomial algorithm is any algorithm that runs in poly-MNL time. There are two classes of polynomial algorithms for linear programs. The first is the ellipsoid method by Khachiyan. It maintains a sequence of shrinking ellipsoids such that it terminates at an optimal face of the polyhedron. The second class of polynomial algorithm for a linear program are interior point methods, first given by Karmarkar and Renegar. It proceeds through the interior of the polyhedron towards an optimal face. The third class for solving LPs is the simplex method given by Danzig. It works by moving from vertex to vertex via edges of the polyhedron until it arrives at an optimal vertex of the polyhedron. It is not known to be polynomial, but it has good empirical performance in practice. Now, differently, an algorithm is said to be strongly polynomial if it uses poly-MN elementary arithmetic operations. So these are your usual plus, minus, multiply, divide, and comparison between two numbers, and it uses poly-MNL space. Note that the number of elementary arithmetic operations is not allowed to depend on the bit length. However, the space can depend on the bit length, and this is reasonable because we need that much space in order to store the input. An outstanding open problem in the theory of linear optimization is whether there exists a strongly polynomial algorithm for LPs. This is also called Smale's 9 problem, and it was first introduced by Megiddo in 1983. Here are some well-known classes of linear programs. The study of strongly polynomial algorithms came from the study of combinatorial optimization problems. And as we all know, many combinatorial optimization problems, such as shortest path, bipartite matching, maximum flow, and min cost flow, can be formulated as a linear program. There is a superclass of such linear programs called combinatorial LPs, and they can be solved in strongly polynomial time by a seminal result of Tardosh. Outside of this class, there are also other known instances of LPs which can be solved in strongly polynomial time, such as LP feasibility with at most two variables per inequality, discounted Markov decision process, and the maximum generalized flow problem. Other classes of LPs which are not known to solve in strongly polynomial time are undiscounted Markov decision process and LPs with at most 2 variables per inequality. I should remark that any LP can be strongly polynomially reduced to one with at most 3 variables per inequality. And in this talk, the main result is to show that LPs with at most 2 variables per inequality can be solved in strongly polynomial time. By a reduction of Hawk-bound, every 2 variable per inequality LP can be strongly polynomially transformed into the following linear program. This linear program has a nice graphical interpretation. Suppose that we're given a directed graph G with node demands B, arc cost C, as well as gain factors on every arc. Then what this problem is encoding is that the inflow minus the outflow at every node should equal to the prescribed node demand BV. Note that the inflow is scaled by the corresponding gain factor gamma E on the incoming arc. So for example, in this picture, the gain factor of this arc is 1/2. So if 20 units of flow enter the arc, only 10 units of flow leave the arc. Note that when gamma E equals to 1 for every arc, then this is just the usual minimum cost flow problem. And for general gammas, this problem is known as the minimum cost generalized flow problem. Having gammas allows one to model a variety of problems. For example, leakages in pipe networks, currency exchange in financial networks, and many other problems. This problem actually appeared in a seminal paper by Kantorovich, which introduced linear programs. And the problem that he was interested in is the following. We have a set of machines and a set of parts that we would like to produce. Machine I can produce gamma ij units of part J in 1 day at cost Cij. And for every part, we have a daily demand of dj. And the problem is to devise a production schedule such that we produce the required demand for each part at minimum cost. This problem can be formulated as a minimum cost generalized flow problem on a bipartite graph as follows. We have the set of machines on one side and the set of parts on the other side. If machine I can produce part J, then we will add an arc from I to J, with the gain factor being the efficiency of the machine at producing that part. Then if we look at this LP, the first set of constraints enforce that we can only use up to 1 unit of every machine. And the second set of constraints enforce that we need to produce at least dj units of part J for every part. And the goal here, of course, is to produce the desired parts with the minimum amount of cost. So what is known about algorithms for solving the generalized flow problem? Polynomial and strongly polynomial algorithms were given for the primal feasibility problem. So this is the problem without cost. We are just interested in computing a feasible generalized flow, satisfying the node demands at every node. Polynomial and strongly polynomial algorithms were also known for the dual feasibility problem. So this is the dual linear program of the minimum cost generalized flow problem. And here again, we are ignoring the costs. We're just interested in feasibility. For optimization, which is the minimum cost generalized flow problem in full, only a polynomial algorithm was known, and this was given by Wayne. So the main result of this talk is a strongly polynomial algorithm for the minimum cost generalized flow problem. And due to the reduction by Hofbaum, this also implies a strongly polynomial algorithm for LPs with at most 2 variables per inequality. And the algorithm is the interior point method recently given by Alamijon, Dadouche, Loho, Natura, and Vey. So from here, I will first provide some preliminaries that we will need for this talk before discussing about the main result. And these are interior point methods and a new notion of complexity for linear programs called the straight line complexity. So before discussing about interior point methods, we first look at central path, which is a crucial object in the study of interior point methods. So let's recall the LP in standard equality form. So minimize C transpose X such that AX equals to be X non-negative. Let's drop the non-negativity constraints and encode it as a penalty function in the objective. So for each xi, for each coordinate I, we will add a log xi term multiplied by a penalty parameter called mu. So as log of 0 is minus infinity, this encourages the optimal solution to this problem to stay away from 0 on every coordinate. Now, because this is a strictly convex objective function, for every value of mu, there is a unique optimal solution to this convex program. So if we denote xCp of mu as the unique optimal solution to the convex program and collect all these optimal solutions, this set of solutions carve out a curve in space, which is called the central path. And as we decrease mu to 0, the central path converges to an optimal solution x star of the LP. And what do a large class of interior point methods do, in particular path-following interior point methods, is that they walk down the central path with geometrically decreasing mu towards an optimal solution. Now let us reparameterize the central path by the optimality gap. So the optimality gap of a point is the difference between its objective and the optimal value. So what we're doing here essentially is replacing the parameter mu by g. So for any value of g, if you look at the hyperplane defined by C transpose X equals to op plus g, the central path intersects this hyperplane precisely at one point. And so this is a valid reparameterization. Now, for every value of g and every coordinate, let us define xi MCP of g as the optimal value of the following linear program. We're maximizing xi such that x is feasible to our linear program, and the optimality gap of this point is at most g. So what this LP is saying is what this LP is telling us is the maximum value that can be attained by the IF coordinate subject to feasibility and optimality gap being at most g. Now, if we collect all the xi MCPs for every coordinate I and every gap value g, this again carves out a curve in space, and we will call this curve as the max central path. It can be shown that the central path is sandwiched between the max central paths. In particular, it is upper bounded by the max central path, and it is lower bounded by a scaled version of the max central path, in particular, scaled down by 1/2m. This means that the behavior of the central path is captured by the behavior of the max central path. So in order to understand the central path, it suffices to study the max central path. One can see the max central path as a combinatorial proxy to the central path, which is a smooth curve. So let's focus on a single coordinate xi and look at the projection of the max central path onto this coordinate. So we will plot the max central path as a function of gap. And the max central path is the upper black curve, which is in general a piecewise affine concave curve. And theta xi-mcp is a scaled down version of the max central path. As we've seen in the previous slide, if we pick theta to be 1 over 2m, then the central path, which is indicated by the red curve, lies in the theta neighborhood of the max central path on every coordinate. Now, what a path following interior point method does is it generates a piecewise affine curve, xlg, near the central path. So since it closely mimics the central path, the trajectory of the IPM also lies in the theta neighborhood of the max central path. Now, we are ready to define the crucial notion called straight line complexity. The straight line complexity of the IF coordinate of the max central path is the minimum number of pieces of a piecewise affine function h such that it lies in the theta neighborhood of the max central path. So here, for example, the straight line complexity is 2 as certified by the blue curve. Since an IPM generates a piecewise affine curve in the theta neighborhood of the max central path, the number of iterations required by any path following IPM is at least the straight line complexity of every coordinate of the max central path. Remarkably, recently Alamigian, Dadouche, Loho, Natura, and Vey designed an interior point method whose number of iterations is the sum of the straight line complexity of every coordinate of the max central path up to a small polynomial overhead. Note that this running time bound depends on the neighborhood size theta. When theta is close to 0, meaning that the neighborhood is big, then the straight line complexity is small, but the log term blows up. On the other hand, if theta is close to 1, meaning the neighborhood is small, then the log term is small, but the straight line complexities can be big. For the minimum cost generalized flow problem, we show that the straight line complexity of every coordinate is strongly polynomially bounded. In particular, if the flow problem is on a graph with n nodes and m arcs, then the straight line complexity of every coordinate in the 1 over m neighborhood of the max central path is O of mn log n. Combined with the interior point method of Alamigian et al., this shows that their IPM converges in a strongly polynomial number of iterations for the minimum cost generalized flow problem. However, to obtain a truly strongly polynomial algorithm, we also have to show how to initialize the IPM in strongly polynomial time, as well as showing how to control the bit complexity of the iterates. I will now give an overview of our strategy on upper bounding the straight line complexity. For every vector f in the kernel of A with positive costs, there is a natural line segment that can be associated to it in the polyhedron. If we start from an optimal solution x star and travel along the kernel vector f, then we move in the polyhedron until we hit the boundary of the polyhedron. And this line segment, xf, will be parameterized by g, which is the gap value. So for any value of g, xf of g is the point obtained by adding a maximum multiple of f to x star, such that the optimality gap is at most g. If we look at the two-dimensional plane with g on one axis and xi on the other axis, then this line segment can be represented as this blue curve. If fi is positive, then as we increase the value of g, the coordinate of xi increases linearly until we hit the boundary of the polyhedron. at which point any further increase in G does not increase the IF coordinate anymore. And so the curve stays flat. So for every kernel vector F, we have this simple curve consisting of at most two pieces at coordinate I. Our strategy for upper bounding the straight line complexity is to find a subset of kernel vectors such that the pointwise maximum of their associated simple curves lies in the 1/m neighborhood of the max central path. And this would then imply that the straight line complexity is at most 2 times the size of the set S. For example, if this is the 1/m neighborhood of the max central path on coordinate I, and these two blue simple curves are the curves for the two vectors in our set S, and that their pointwise maximum lies in the neighborhood, then one can see that the straight line complexity is at most 4, because every vector in S induces at most 2 linear pieces in the resulting pointwise maximum curve. And the resulting pointwise maximum curve is piecewise affine. To conclude, we have shown a strongly polynomial algorithm for LPs with at most 2 variables per inequality. The same algorithm also works for LPs in standard equality form. So minimize C transpose X such that AX equals to B, X non-negative, when A has at most 2 non-zero entries per column. This is because the IPM of Alamijian et al. Is a primal dual interior point method. Now, one might wonder whether the straight line complexity of every LP is strongly polynomially bounded, and if so, this would give a way to resolving Smale's 9th problem. Unfortunately, there is a negative result by Alamijian, Benchimo, Gobier, and Josvik, which shows that there exists LPs with exponential straight line complexity. Recall that IPMs can solve linear programs in polynomial time. So this necessarily implies that the numbers occurring in these LPs are doubly exponential in the size of the matrix, M and N. I will conclude my talk with some future directions for research. The first open problem is to determine the straight line complexity of undiscounted Markov decision processes. As we've seen in one of the previous slides, the strongly polynomial solvability of this class of LPs is still open. For the next direction, now that we have a strongly polynomial algorithm for min-cost generalized flow, a natural next step is to design faster strongly polynomial algorithms for this problem. Another interesting avenue of research would be to give a strongly polynomial combinatorial algorithm for minimum cost generalized flow, where by combinatorial, I mean that the algorithm is not based on interior point methods. Thank you very much for your attention.